the webinar is basically for people who are relatively new to Hadoop, and just to give everyone an idea of what the hype is all about around Hadoop, what is Hadoop useful for, just looking at some of the requirements and the use cases in which Hadoop can sort of be useful within your organization. And the second part, which will be on Tuesday, we will be discussing some of the basic concepts of what that are implemented within Hadoop. So these are just for people who want to understand a bit more about Hadoop. It's not for people who already have extensive Hadoop experience, and just sort of touches up on a high level on the basics of Hadoop. Yeah, it's a very short webinar, about an hour. If you have any questions, just feel free to post them in the chat, and I will try to address them as much as possible. Just a bit about OSS Cube. We are an open source company, traditionally focused on PHP and MySQL and some other PHP related technologies such as content management systems, Drupal, Joomla, but also Sugar CRM and things like that. Just recently, since half a year ago, we've became a Cloudera partner. We are the Cloudera training partner within India and part of the Asian region. So, been giving trainings around Hadoop and some of the products within the Hadoop ecosystem for the last 2 or 3 months. Yeah. So let's get started. So motivation for Hadoop. So before you get started with Hadoop, it's obviously we need to understand what Hadoop is good for. Does it really fit within my organization? Do I have a proper business case for it? Yeah. And so what we're trying to address here in this first part of the webinar is to find out the problems that Hadoop is actually trying to solve. So we'll be sort of looking a little bit about the history of large-scale computing, and then we'll go through some of the requirements that we try to fulfill when we're looking for an alternative approach. Yeah. So traditional computing. Now, not too long ago, when we were talking about large-scale computing, basically was focused on processing. Yeah, we had this huge, big servers, mainframes, and it was all about processing power. And these computers, they were sort of processing relatively small amounts of data. But the processing was very complex, yeah, and therefore we needed a lot of processing powers, and therefore it was focused in the past on sort of really increasing the processing powers. And we all know this race of processing power that was going on between the different chip companies like AMD and Intel. And we also know the law of Moore, where they say, okay, the processing power will sort of double every few years or so. And so this was the main focus on large-scale computing in the past. If you needed to more processing powers, you added extra CPU power to it, or you bought a bigger computer, and it was all about scaling up vertically. Yeah, and by scaling up vertically, I mean you just bought more hardware, you bought a bigger computer that could deal with your problem. This was the traditional way of dealing with large-scale computing. You bought more RAM if you needed to process a bit more data that didn't fit in the RAM. This was the traditional way. Yeah. Now, with Moore's law stating that the processing power doubles every 2 years, well, we've been quite a few years now in the future, and processing power is not such a big problem anymore. Yeah, we have a lot of processing power, and what we've noticed is that, especially since the .com era, a lot of data has started to being produced. We all know these Facebooks and the Googles and the Twitters. They produce a lot of data. So it wasn't so much about processing power anymore. It was more also about storage. Yeah. And the traditional, the front runners of the traditional distributed computing, like MPI, PVM, Condor, these were sort of the distributed systems of the time. They didn't cut it anymore. They sort of were very, very complex systems to implement. They were focusing on processing power, and the learning curve was very, very steep. So all these traditional way of dealing with distributed computing were very, very complex. So the problems that we had with these traditional distributed systems is, like I said, they were complex. Data exchange requires constant synchronization. I'm not sure if any of you have worked with things like clusters, or in the past I've been doing some programming with Corba and RMI. It is a lot of complexity. Yeah, the data needs to be in sync everywhere. There is a lot of overhead of communications between the different nodes or the components of the system. And if one of the systems failed, then the whole system failed. I remember one of my first projects where we written a system for an insurance company which was based on components, components. And we've implemented these components that they could be sort of independently run on different computers, so we could scale out the hardware. And so we had like this 4 or 5 computers on which these different components were running. But the problem there was that if one of these computers failed, then the whole system was down. And then we had all the overhead of maintaining all these different components, which sort of was a lot of work, and it costed a lot of money. So it was, to be honest, that project was a bit of a headache, but it sort of highlights the traditional way of distributed computing. Yeah. And so one of the requirements that we realized early on in that project is the more hardware you add to your distributed system, the more chance there will be that one of those hardware components will fail. So if you start building a distributed system, you need to be able to cater for hardware failure. It is inevitable. Some component will fail at one time or another. Yeah. So this is when you design a new distributed system, you need to be able to cope with hardware failure. This is one of the main sort of requirements for the new to be designed distributed system. In the old days, it sounds like it's very far away, but in the traditional way of distributed system, you will have all these different computers which will have a lot of computing powers, and all the data is stored centrally on the SAN. And so these systems will access the data through the SAN. Yeah. However, the SAN generally is also very high quality storage. They often cost a lot of money. Your average SAN will generally cost you over $10,000 if you want to have a high quality SAN. Yeah? And what happens is then these distributed systems will then copy the data from the SAN, transfer it locally to the node, and then start to do your computing. Yeah? And so this works fine for very limited amounts of data. To give another example, I'm not sure if any one of you knows about the SETI project. Yeah? This was a very, very popular project about 10, 12 years ago. And basically the SETI project is a project, it's called Search for Extraterrestrial Intelligence. Yeah? So what they've done is they've gathered all this huge amount of data, yeah, from the telescopes, yeah, and then they just trawl through that data to find some evidence that might point to extraterrestrial intelligence. But their systems couldn't cope with that amount of data. So what they decided is they wrote a little program which normal people around the world could download, install it on their local computers, and run it as a screensaver. And if your system is not doing anything, you're out for a cup of tea or whatever, it goes into screensaver mode. What it then would do, it would grab a chunk of data from the central SETI system, copy it locally to your computer, and then start crunching away. Start doing the processing and the analytics on the data. So this is a good example of a very traditional way of distributed computing. All the data was stored centrally within the SETI system, but what they've done, they've written a little program which sits on the home user's computer, and the home user's computer then from time to time goes and fetch a little chunk of data and starts processing it on it, and then sends the results back. Yeah. Now this worked very, very well. The efficiency of SETI just skyrocketed because obviously they suddenly had this millions of people installing this new screensaver on their computer, and they were able to cope suddenly pretty well. Yeah. Now this is a good example of traditional way. However, this works only for very, very small chunks of data. And even 10 years ago, the broadband or internet connections were not sort of very good. Speeds were much slower than they are nowadays. So they only could copy little chunks of data to the user's computer, do the processing, and little chunks of results are sent back to the SETI central computers. So this would work very well. But if you need these computers, these nodes, these desktop computers to do processing on big, much larger chunks of data, this would not be acceptable. Yeah, because the bandwidth is limited, and can you imagine millions of people downloading huge amount of data from the main computers? That would really bring the networks down. So this is a sort of an example of the traditional way of doing things. Nowadays, things have changed quite a bit, yeah. Especially since the whole .com era. The amount of data being produced every single day is massive, yeah. Especially the online systems, the social networks like Facebook, Twitter, you name it. They just generate massive amounts of data. Now, these data, you cannot just throw away. They need that data. They need to do analytics on it. They need to process it. All sorts of things they need to do. But the traditional way of computing, one big computer to process all of that, it's not possible anymore. Yeah. So there needs to be new ways of being able to cope with these large amount of data. Yeah. Examples: eBay, for instance. So many people buy stuff. All these auctions going on. You need to be able to process that amount of data. And not just online organizations. Banks, for instance, they have millions of transactions every single day. And these transactions also need to be processed. They need to be analyzed and all of sort of these things. So we need a new concept to be able to cope with these massive amounts of data. We're not talking terabytes anymore. We are talking petabytes. Yeah, I think the size of a disk nowadays is what, a few terabytes. So can you imagine if you just want to store a few petabytes of data, how much disks you need in order to cope with that data? So now it's not so much the processors that's the bottleneck anymore, the processing power. It's more the data that is becoming the bottleneck. Can you imagine to sort of move a petabyte of data to to your processing unit to process that data? It is not realistic anymore to do that. Yeah? Just some simple calculation here is that a typical disk transfer is 75 megabyte, and I'm just talking the normal disk platters. I'm not talking about the SSD, solid state disks, which have improved much more in speed. But most of the disks are still the normal spinning disks, because the SSDs are normally high-end kind of storage. So if you have a normal disk and you want to transfer 100 gigabyte of data from your disk, so you just want to read it, yeah, and then pass it through your processor, it takes about 22 minutes, yeah. And this is a sequential read, yeah. So assuming that this 100 gigabyte is just one single file which can be sequentially read, and it's not read, and it's not fragmented. Yeah. So this is sort of gives you an indication of what the bottlenecks are in dealing with large amount of data. Another thing is that this whole, if you want to process 1 gigabyte of data, you cannot fit that in your RAM. Yeah. The RAM is very, very limited. So you need to somehow find a way to be able to process this 100 gigabyte of data without sort of flooding your RAM. So we need something new. So what do we need? What are the real requirements? So looking at the past, the traditional way of doing things, yeah, what are we looking for? Like I mentioned before, in distributed computing, when you're working with multiple computers, there bound to be failures. Yeah, there's bound to be some hardware component somewhere or another that will fail. Yeah, and so you need to be able to cater for that. And if it fails, it is not acceptable that your entire system fails. Imagine you have a cluster of 100 nodes and just one component fails, and then all the other 99 servers can't work because of this one single component failure. That is not acceptable. So we need to be able to cater for that. Component failure means the system still continues working, but maybe with a graceful degradation in performance. Yeah, because there are a few nodes that are stopped working, and obviously we need to be able to cope with less hardware, but the system needs to be able to continue. Yeah, without affecting the results. If such a component fails, it is not acceptable that you lose any data. Yeah? Can you imagine that the bank has a cluster, a few of the components fail, and then suddenly a few transactions get lost? Yeah? And these transactions may contain a few $1 million in transfers. It is not acceptable to sort of lose any data. If you lose a component, the data should be still within the cluster somewhere, and the system should pick up that data and start working with that. If the component has failed and the sysadmin or whoever fixed that component, or that component is replaced, you should be able to sort of plug in that component without restarting the entire system. Even more so, if you notice that your system is the performance requirements, the storage requirements of your systems are growing over time, you need to be able to extend, to scale out your cluster by adding new nodes, new components to your cluster without having to restart the entire system. So you can grow your cluster without, and it just continues running without any stops or restarts. In addition, that if you have a cluster and say, for instance, you run some jobs or some processes that are crunching away at the data. Yeah. Now suddenly a component fails on which one of these processes were running. Yeah. It should not affect the outcome. And even furthermore, it should theoretically also not affect the execution. The job should be able to continue or restart somewhere else and continue as it was before without any change in the results. Yeah, the results should be the same as it would have been in case the component didn't fail. Yeah. So those are sort of a few of the examples of the requirements that we have in mind in sort of designing a new distributed system. We mentioned a few. There should be a graceful decline. If you sort of add another job, the cluster should be able to cope with it. You can sort of process multiple jobs. This is what it's all about. You have multiple nodes, so they can start processing in parallel. But never should it lead to a failure within the system. And one of the main requirements also is that, especially if you look at these online companies like like eBay, like Facebook, like Amazon, they produce a lot of data every day, yeah? And so you need to sort of be able to grow as the data grows, to grow as the processing performance requirements grow. And you want to grow linearly, meaning that if I add twice as much resources into my cluster, I want to have twice as much storage capacity. I want to have twice as much processing capacity. Yeah? And this way, I can sort of grow my cluster as my business grows, which is very nice because I can start out small, and then as my business grows, I invest in more hardware. I don't have to upfront buy a big computer or a lot of resources with a lot of money, which initially will only sort of be utilized 10% of the capacity. Yeah? So I want to sort of be able to start out small and then scale out, grow as my requirements, as my business grows. Yeah? So I increase the capacity proportionally, linearly. These are sort of the requirements. Now, so how do we solve this problem? How do we implement the solution for these kinds of requirements? This is where Hadoop comes into play. Yeah. Well, in the early 2000s, we all know Google started in the late 90s. And they became very, very popular amongst the internet crowd in a very, very short time. And they quickly sort of ran against this wall of hardware limitations and traditional distributed computing. And so they did a lot of research in how to solve these problems we just discussed before. And in 2003, they published a paper which is called GFS, about GFS, their Google file system. Yeah? And a year later, about a year later, they published a paper about MapReduce. So these two papers were addressing some of these issues that they were coping with, some of these issues that we described earlier. And at the same time, within the Apache project, there was one other developer, a developer who was running against the same issues that Google was running into. And he sort of started to search around. His name is Duck Cutting. And he came across these Google papers. And his immediate thought was, this is what we need. And so he started an open source implementation of these concepts that Google published. Now, these sort of concepts that Google were talking about took a completely new approach into solving the problem of distributed computing. Yeah. When he read this paper, he immediately saw that what Google was talking about were addressing most, if not all, of his requirements regarding scalability, reliability, and all of that. Yeah. So, what was it that this paper was talking about? The main concept, yeah, is all about computing power, that the data is stored locally and on the places where the computing actually takes place. Yeah. Remember, in my SETI example, you copy the data from a central computer that is transferred across the network all the way to your home computer, and then processing takes place. Yeah. Within the Google file system and MapReduce concepts, basically what it says is that we're going to distribute the data across all these different nodes in my cluster, and then once they're distributed there, I don't move the data around. They sit there. If I need to process this data, I do the processing locally where the data sits. Yeah? So I don't have to copy a data set from one node to another or anything like that. No. I locate where the data sits that I need to process, and then just distribute my little program to that process and to that node where the data sits and process the data locally. So there is no data or minimal data transfer across the network. This is sort of the core concept of the GFS system. Yeah. Now, how do I process this data? So the idea is that developers write this little high-level program codes, yeah, and what they then do is they sort of then distribute, they submit that code to the cluster. The cluster then identifies, okay, this code, on which data do I need to sort of run this little application. It locates the data within the cluster and then copies that little program to that node where the data sits, and that little program then starts crunching away at the data that sits locally at that node. Yeah. So instead of moving the data around, what I now do is I move my application around. But my application is basically a very, very small piece of data. It's usually not more than a few megabytes that I need to move around, whilst data are gigabytes and petabytes that I move around. So this is a very good trade-off. So instead of moving my data around, I just move around this little application. And the application then crunches away at the data that sits on that node. And all these applications are running on multiple nodes at a time. So one data set sits on one node, another part of the data set sits on another node, and another node, etc. And so this program can then be distributed across multiple nodes, and it will then crunch away at the data in parallel. Yeah, and then the results are then gathered in one place again, which will require some copying, but the results set, the amount of data is generally much less than the input data. Yeah, and so the aim of this whole concept is that the nodes, they communicate with each other as little as possible. I submit my job, a program is copied to a node, it crunches away at the data locally, does not communicate with anything else, and only sends back the results. Yeah, that is the whole idea. Yeah, and developers developing this programming, these programs for Hadoop, they need to keep that in mind, that there is no communications between nodes. Yeah, and so if I look at Hadoop, the design is basically twofold. One is the file system, which is called Hadoop Distributed File System, HDFS, which basically takes care of all the data. If I put my data in the node, what happens? It takes the data and distributes it and replicates it across multiple nodes. So remember when I said that if there's a node failure, that I should not lose any data, that is because the data is replicated across multiple nodes. So if one node goes down, that data that was on one node sits somewhere else in the cluster on another node. All that needs to happen is that Hadoop, the system, needs to sort of identify, okay, which data was sitting on that node. That node is now not available anymore. Where does the data is in the where's the rest of the data that within the cluster that was on that node? find it, and then send that little program to that node and start processing there. Yeah. So even though one node is down, I can still find the data, the same data somewhere else in the cluster, and then can start processing again. Yeah. So this is sort of one of the really important benefits of the Hadoop implementation. Yeah. And in essence, if you don't need history, or Hadoop automatically sort of serves as a backup system. Yeah. So I just copy my data in there. I don't have to make any backups, because I know that even if there are hardware failures, I can retrieve that data from some other node. Yeah. So there is some inherent backup taking place within the system, obviously saving you some money on implementing backup systems as well. And for history of backups, you don't have to worry about, because Hadoop can handle such large amount of data, you just keep adding the data, and you don't have to throw away anything. So in just a high-level overview, remember in part 2 we're going to go into a bit more detail of these concepts which I'm explaining now. Yeah, but this is just to give you some fragrance of how it works. When I have this huge gigabyte file that I sort of load into Hadoop, which I want to do some processing on, some analytics on. When it's loaded into Hadoop, what Hadoop does, it chops that file up in blocks. It splits it into blocks, yeah. And typically, the size of such a block is either 64 megabyte or 128 megabyte. It's configurable, but these are generally the default settings. It chops it up into these chunks of data, and this data is then spread across the cluster and stored on the different nodes. And each single block is replicated by default, again configurable, 3 times. So if one node goes down and it has one chunk, one split of my file, then there are 2 other copies of that same chunk of file sitting somewhere else in my cluster on one or another node. Yeah. So even then, if one of the other node goes down, I still again have another copy. Yeah. So this is one of the basic concepts, the way HDFS works, splitting it up and then spreading it across the cluster and replicating it by default 3 times. The programs, so I have loaded this gigabyte of file into the system. It's chopped up in these little blocks of 64 to 120 megabytes, sits somewhere in my cluster. Say if I have 120 megabyte blocks and I upload 1 gigabyte file, then I have around probably 7 to 8 blocks, right? So what it then does, it sort of copies these blocks across different nodes. Say it could be 7 nodes, and then also replicate it 3 times. And then if I want to process this data, yeah, the developer then writes a little program, a MapReduce programs. And so what happens is this program then gets distributed to each of these nodes where these blocks sit. So in my example case, if this data is spread across 7 different nodes, this little program, which is only a few megabytes large, is then copied to each of these 7 nodes, yeah, and then starts to crunch away at that one block of data, this 128 megabyte data. It crunches it away, processes it, and then sends the results back. Yeah. So MapReduce is sort of part of two-phase program, the map phase and the reduce phase. We'll come into that into detail in the next webinar. But for now, just on a high level, the map phase just grabs one chunk of data and then processes it. So each map, in this case, I will have 7 mappers working in parallel, yeah, and then giving me the results back. So each mapper will work on one single block, yeah. So can you then imagine 7 working in parallel? Instead, if I had one big computer, I would have needed one big computer that runs on that whole gigabyte. But now I have 7 computers working on just 120 megabytes. So this is the difference with traditional way. Everything is processed and stored in parallel. Now, say in my example that if one node fails, yeah, so I have these 7 nodes that are working. My cluster can be much bigger than that, but because the file is only 1 gigabyte large, the data is spread only across 7 nodes, but I might have some 20 node cluster. Now, if one node fails, yeah, that was working, I submitted my job, they're crunching away, 7 nodes are crunching away, suddenly one of the 7 nodes goes down. What will happen? Hadoop will automatically sort of notice that and says, okay, this node is stopped working. And then it finds another node where the same data sits that was on that one node, submits that job to that node, and executes that job again. Yeah, and then that job starts running on that other node. Yeah, so this is how Hadoop sort of tries to cope with node failure. One node that fails does not affect any other node at all. Yeah, the only effect that it has is that well, the total job execution might take a bit longer because now Hadoop needs to find another node, submit the job on that other node, and obviously that job started later, and so we have to wait till that node finishes. But also, obviously, then the total performance may decrease. In this case, it may not, because we still have 7 nodes working in total. Yeah, and so restarting and all of that is all automatically. The administrator has to do totally nothing. If it goes down, Hadoop takes care of all of that. The only thing that needs to be done is some sort of notification sent to the administrator, or saying, look, some node is down. I'm still crunching away. Nothing is wrong, but please have a look at this node. And so the administrator then goes in and check what is wrong, fix whatever needs to be fixed, and then can sort of rejoin that node if it's sort of fixed without any interruption in the whole overall system, even without any interruption within the job that was executing at that time. The only thing is the job took a little bit longer, but that's okay. So this is basically, in a nutshell, sort of the motivation for Hadoop, why we have any, where Hadoop comes from. So the background, the traditional way of solving the problems, which requirements that Hadoop actually implements that we are currently coping up. It's the shift from really limited processing powers to shift to limited storage and limited processing, being able to process only limited set of data. So this is where Hadoop sort of comes in, the whole shift from processing power to storage, the way it's stored and the way data is stored. Not moving the data to the processor anymore, but moving the program or the processing logic to where the data sits and doing the processing locally. And this allows me to easily cater for all these requirements, to easily scale out linearly. Like if I double my nodes, my capacity, storage capacity is doubled and my processing power is doubled because I can do all of that in parallel. And the nice thing I find about this, because I've done some distributed programming in the past, you don't have to do all that plumbing. In the past, when I did this programming on this limited small distributed program system, is that you need to do a lot of plumbing. You need to write your own synchronization mechanism. You need to within your program check on sort of whether the system is still alive. You need to check the heartbeats and all of this plumbing, and which takes maybe 80% of your time, and then only 20% of your time you're left with actually implementing the business logic, focusing on the business problem. Hadoop takes away all of that. All that infrastructure, all that plumbing is done for you. They gave you a simple set of interfaces which the developer can start to work with and immediately start focusing on the business problem. That is the whole nice thing about the infrastructure. So with this, I want to sort of bring an end to this presentation, this webinar. If anybody has any questions, feel free to type it in the chat and I can address them for the next 10 minutes or so. Or on Tuesday, I'll go, if there are a bit more detailed questions, more technical questions. In the next session on Tuesday, I will go a bit more deeper into the concepts of Hadoop and how they are actually implemented. Yep. Any questions so far? Okay, so I've got a question here. What are changes? Sorry. Let me just get here. Okay, so I have a few questions. So first question is by Sandeep. Here we say replicated data multiple times on the system. Doesn't this cost more money for infra? Yes. The answer is yes. If you can imagine that the data is replicated about 3 times, so that means you will lose 1/3 of your storage. So you need to cater for that. extra storage. You need that extra overhead to be able to replicate the data. However, having said that, is that Hadoop aims to sort of to utilize low-cost hardware. Yeah, instead of this high-end, very expensive computer systems, you should be able to use commodity hardware. No expensive SANs are needed where the hardware, the hard disks, the storage system is very, very expensive. You can use normal commodity hardware, normal cheap servers in the range between $2,000 and $4,000 you can use. And so even though it costs extra money, it doesn't sort of, it doesn't require you to really buy high-end hardware. Yeah, so in that sense, it is cheaper, but yes, replicating data costs extra money, but at the same time, it is also kind of a backup. Yeah. What happens if the master goes down? Yes, good question. If the master goes down, your cluster is down. Yeah. So the master you need to take care of very well. So this is the one part in your cluster that does require high-end computing. It's a high-end hardware because you want to maintain that. But the data nodes where the actual processing takes place, those are very, very cheap, low-cost commodity hardware. Yeah. I hope that answers your question, Ashwini. Another question from Sandeep. Is parallel distributed computing the same? I'm not sure I understand that question. The same distributed computing. Okay, parallel. In a sense, yes. Distributed computing basically says that okay, my storage and computing power I distribute across multiple nodes, and parallel means they work in parallel. So in a sense, you can say yes, they're sort of the same. In this case, yeah. What happens if the master server goes down? Yeah, I've already answered that. Currently, reliability, like I said, reliability about the master server, make sure you have a high-end hardware there that does not fail easily. The older versions of Hadoop, sort of, you need to make sure you cater for it. You need to make sure you have some hot standby server that if the master server goes down, you can bring up another one easily. But all of that stuff you had to do by yourself. However, in new versions of Hadoop, they sort of implementing some new features which sort of implement high availability of the master server by default, which allows you to sort of, if one server goes down, then the other one takes over. So that is coming up in new versions of Hadoop. What are changes of using Hadoop in banking and insurance sectors by Nagraju? One of, I assume you mean the use cases, yeah? So how to use Hadoop, where are the uses, what are the use cases, right? So basically, I have not done many projects in that area, but from the feedback I get from the community is basically that Hadoop in the financial systems and also insurance system is used a lot for fraud detection. Yeah, so all these transactions, all these claims, they are sort of going. They processing and analyze all this data in order to detect fraud. So this is one of the main uses currently in those branches, what I've heard of. So hopefully that answers your question. Another question from Bala. How different is what you presented from the SETI project itself? Here to Hadoop expect the results back to trivial. Yeah. So basically, the difference within SETI is that you move the data around. Yeah. Within Hadoop, you load the data and it sits on the node and there is it. Finished. The data does not move again. Then what you do is you move your program to where the data sits. Now, in case of SETI, okay, you copy the program as well, but it's a fixed program, and the program then sits and it's on that computer and doesn't move. And then what happens is then they keep pushing data to your computer where your program sits. So in that sense, yes, you make sure the software is installed on the node that you want to do the processing, but you move the data to all those different programs. So there's a lot of data moving around, copied around. So that's basically the main sort of difference between the SETI example that I gave and Hadoop. So question from Mohammed. How can we replicate 3 replicates in different racks and 3 different geographical locations? So basically, very good question. Hadoop has a feature that is called rack awareness. Now, this is quite important if you have huge data centers with large clusters, like 100+ nodes. Yeah, and so you want to have this this rack awareness, because what can happen is that a rack goes down. Yeah, so your whole rack sort of goes down, either power failure or whatever, switch failure, whatever. Yeah. And if sort of all your data sits within that one rack, you lost your data. Yeah. And so basically with Hadoop, you can sort of pass your whole data center configuration with all the racks. You can sort of pass that to Hadoop. So Hadoop knows sort of the locations of the servers, how the racks are configured, which server sits on one rack. So it will never copy all 3 replicas of that data in one rack. Yeah, it may copy 2 replicas of the data in one rack, because then there is a sort of because you have local communication within the rack is very, very fast, but never all 3 replicas. Yeah, the 3rd replica will then be copied to another rack. Yeah, so this concept of rack awareness exists within Hadoop and allows you to sort of tell Hadoop not to copy everything in one rack. And if one rack happens to sit in another location, then it will take that into account. But obviously, if you're talking about different geographical locations, you need to be very careful with the network connection you have to between these 2 locations, because you don't want to flood it when it's trying to sort of copy all the data across to the nodes in another location. Yeah. So hopefully that answers that question. Another question from Bala. What are the IP intellectual rights around usage, specifically the license to use it in commercial software? I am not much of an IP specialist, but Hadoop is open source software, part of the Apache projects, which allows you to use it freely. It is subjected to the Apache license, but the details of the Apache license I don't quite know, to be honest. I'm not sure. I don't think it's a big issue if you want to use it in commercial software. But for that, I would suggest you sort of just have a read through the Apache license. Another question from Sandeep. Can Hadoop be used for image processing? Yes, it can. You just store the images on your cluster in HDFS. Yeah, and you just have to write a MapReduce program which can sort of interpret the images. So yes, you can do that. That's not a big problem, as long as you are able to write the software to process those images for you. Mohammed again, to sort of more specifically his question, you want to put I want to put each replica in each rack. Yeah, it is completely configurable. So you can configure how sort of Hadoop should treat racks. However, yeah, if you really want to do that, I'm not sure, because the default the recommendation is that by default you have at least 2 copies on one rack, because then sort of in the reduce phase, what needs to happen is some data needs to be copied between nodes. So there is some data being transferred. And this happens much more faster within one rack rather than across racks. Remember that inter-rack communication can be a bottleneck. So if you can do some communication that is that stays within one rack, the network performance will be much better rather than overloading the inter-rack communication. Yeah, but yes, you can. All right, I think that is the last question. I hope you enjoyed it. If you're interested in more detailed about the concepts, how they are implemented in Hadoop, please join us for the next session on Tuesday, the same time, part 2 of the Hadoop Essentials. Yeah, thank you for joining. And then I think I'll close this session now. See you next time.